Today I will talk about linear regression. It is part of my lectures on machine learning. This is my lecture outline. First I will talk about machine learning. Then I will give introduction to linear regression. Then I'll talk about assumptions of linear regression. Then I'll talk about types of linear regression. Then I'll talk about mathematical model, followed by problems, model performance, model diagnostics, and I'll give an example of linear regression in Python code. So machine learning is a branch of artificial intelligence that focuses on the development of algorithms and statistical models, which can learn from data and make predictions. Machine learning can be supervised or unsupervised. Supervised learning are of two types: classification and regression. Classification predicts the class of the dataset based on the independent input variables. Class is the categorical or discrete value. For example, logistic regression. I have a full-fledged lecture on logistic regression on my channel. The regression predicts the continuous output variable based on independent input variable, and example is linear regression and its variants. Linear regression is a type of supervised machine learning algorithm that computes the linear relationship between a dependent variable and one or more independent variables known as features. When the number of independent feature is 1, then it is known as univariate linear regression. In case of more than one feature, it is known as multivariate linear regression. Linear regression is relatively robust to outliers compared to other machine learning algorithms. Outliers may have a smaller impact on the overall model performance. However, linear regression is susceptible to both overfitting and underfitting. These are the assumptions of linear regression. First assumption is linearity. The independent and dependent variables have a linear relationship between one another. Second is independence. The observations in the dataset are independent of each other. Then homoscedasticity. Across all levels of the independent variables, the variance of errors is constant. Normality. The residual should be normally distributed. Multi-collinearity. There is no high correlation between the independent variables. So multi-collinearity should be absent. So these are assumptions that there should be a linear relationship, the observations are independent, and the variance of the error is constant, and the residual should be normally distributed, and there should be no multi-collinearity. Then types of linear regression. As I have discussed, there is a univariate linear regression and multivariate linear regression. Then there is polynomial regression. In my today lecture, I will give an example of polynomial linear regression. Then there is ridge regression, lasso regression, and elastic net regression. Lasso regression also performs feature selection. Then mathematical model. This is the univariate linear regression model. So this x is independent variable and y is dependent variable. This is multivariate linear regression, x1, x2, and similarly these are independent variables and y is dependent variable. In matrix form it is written as this. Then solution in matrix form, these are the coefficients which can be derived from these matrix operations. Then multivariate linear regression with polynomial terms. So we have, for example, let us say we have two variables. Then we have term for variable 1, square term of variable 1. Then we have term for variable 2, square term of variable 2, and interaction term of variable 1 and 2. and these are the coefficients, all betas, and this is intercept, this is dependent variable. This is the example of polynomial linear regression. So ridge regression, in ridge regression, we have this cost function. I'll talk about cost function a little later. So we have this penalty term in cost function, and this is known as L1 norm penalty, and it generates a sparse model. This is lasso regression. We have cost function, and this is the penalty term. So L2 norm penalty results in feature selection. And combination of these two penalty terms in this cost function results in elastic net regression. So here L1 norm penalty generates a sparse model as in ridge regression. L2 norm penalty results in feature selection as in lasso regression. And in addition, it also encourages grouping effect and stabilizes L1 regularization part. So what is cost function? Actually, these are cost functions. So what is cost function? The cost function or the loss function is nothing but the error or differences between the predicted value and true value. And one such measure is mean squared error. Then how do we estimate the coefficients? We estimate by the method of gradient descent. A linear regression model can be trained using the optimization algorithm, which is known as gradient descent, by iteratively modifying the model's parameters to reduce the mean square error of the model on training data set. So this is how we estimate the coefficients of the model. Then problems. These are the problems. There may be a problem of outlier. An outlier is defined as an observation that has a large residual. Hence, the observed value for this point is very different from that predicted by the regression model. Then leverage point. A leverage point is defined as an observation that has a value of x that is far away from the mean of x. Influential observation. An influential observation is defined as an observation that changes the slope of line. Then multi-collinearity. There is high correlation between independent variables. Then there is a problem of multi-collinearity. It is assessed by variance inflation factor. If VIF is equal to 1, it means no correlation. If it is between 1 and 5, it means moderate correlation. If it is more than 5, it means severe correlation. And VIF can be between 1 to infinity. So we need to remove the variables which are correlated with each other. Then model performance. We assess the model performance by one of these. One is mean absolute error. It measures the average absolute difference between the predicted and actual value. Then mean squared error. Measure the average square difference between the predicted and actual value. Then root mean squared error, the square root of the mean squared error. Then coefficient of determination or R squared, a measure of how well the model explained the variation in the dependent variable. So R square is defined as 1 minus regression sum of squares and total sum of squares. And adjusted R square, it is adjusted for number of the input features or variables. So this is the concept of sum of square. Explained sum of a square is defined as this difference between predicted values and mean vector of outcome variable or dependent variable. Then residual or regression sum of squares, it is the difference between outcome value and predicted values of outcome. Then total sum of squares, it is defined as difference between outcome values and mean of outcome value. So total sum of square is equal to residual sum of squares plus error sum of squares. And this is the graph depicting the residual sum of squares, and this is the graph depicting the explained sum of squares. Then this is F statistics. So it is the difference in numerator. There is difference between the residual sum of squares of restricted model minus residual sum of squares of full model. So residual sum of square of full model is always less than that of restricted. And how much improvement is there as compared to full model? So this is the F statistics. So we can compare any two model using this F statistics with degree of freedom K and Nk minus 1. Then F test for all coefficients. This F test is different from this F statistics. In this F test, it is defined as uh, explained variance divided by unexplained variance, and this is nested F test. And F test can also be written in terms of R square. In the various libraries of Python language, we get R square. So from that R square, we can calculate the F test for coefficients. Then this is the T test for individual coefficients. It is defined as this, where standard error of coefficient is defined as this. Then standardized coefficients, all input variables are on equal footing. So one can compare the strength of effect of the input variables. So it is defined as this. However, it is important that as variance will differ across different samples, the standard coefficients cannot be used for comparison across samples. Then model diagnostics. Objective is to investigate if the calculated model and the assumptions we made about the data and the model are correct. It includes graphical and numerical tools. It also checks outliers and collinearity. So these are the diagnostic plots, residual versus fitted value plot. It is to assess the linearity and homoscedasticity. Then QQ plot, it is for testing normality assumption. Then scale location plot, that is square rooted standardized residual versus predicted value. This is for homoscedasticity. Then Cook's distance, this is for influence. Then identification of leverage point. Then information of influence function. Then partial residual plot for non-linearity in relation between y and individual input variables. I will give you example of many of these in my Python code today. Then overall process of linear regression is, first of all, we process the data. Then we do feature selection by using correlation statistics or mutual information statistics. These are all available in sklearn library of machine learning in Python language. Then we fit the model. Then we do the model performance estimation. Then we do model diagnostics. So this is the Python code example. These are the libraries which we'll use. So first library pandas is for data frame. Then the NumPy library for mathematical operations. Then these sklearn libraries for linear regression. And I'll do polynomial regression in my today's example. Then this is the data set, inbuilt data set in sklearn, iris data. Then these libraries, stats model and yellow brick, these are, I will use these for model diagnostics. Then this is the graphical plot library, matplot library. So we load the data. So we first extract iris data from the sklearn. Then we convert the iris data into pandas data frame by using this code. This is our data. Then this is the polynomial regression. First, we split our data into train and test set. Then we, by using the pipeline, we use two steps. First step is to making the features in a polynomial terms. These are various features in polynomial terms. There is a square input variable and there is also interaction variables here. And the second step is linear regression itself. So there are two steps. First is polynomial features. The second is linear regression in my example. And this is the model score. Then this is model performance. We have calculated mean squared error, mean absolute error, R square explained variance score, mean pinball loss, D2 pinball loss, and D2 absolute error score. So this is about model performance. Then this is the plot between the actual and predicted values. So this is the model diagnostic. So first of all, for linearity and homoscedasticity, we have plot the residuals versus predicted values. So it is actually showing that the variance is not same across all levels. It is different. So our model is not appropriate, in fact. So assumption is not good. Then this is for normality. We have this QQ plot here. We have used yellow brick library for this. Then this is the histogram again for normality. We have used visualizer of yellow brick library. Then this is Cook's distance plot. So we have these five observations above the threshold, influencing observations or influential observations. So this Cook's distance is again using yellow brick visualizer. Then these are the actual Cook's distance as calculated using the stats model library. Then this is the these four observations are actually above the threshold in Cook's distance. So these are those observations behind the Cook's distance, which is more than the threshold. So these are influential observations. Then this is the test simple coding to identify the outliers. So we use standardized residual here, and we have identified that this observation, particular observation is an outlier. So now this is model output. So we need coefficients. So these are the coefficients of polynomial terms. So they are total 10, and these are the p-values for individual coefficients we have calculated using this code. So this is all for today. Thank you very much.